Welcome to the glass plate. In this example we're going to take a look at drag force on autoes. Let me sketch one. This obviously is a not so streamlined car. And the first cars, like the T Ford, started with relatively big frontal area. Modern cars are much more like this. They are streamlined and have a lower frontal area. What we would like to do in this video is find out how that influences the mileage of a car. The mileage is the amount of gasoline used per 100 kilometers, or rephrased, the amount of energy used per unit of length. If we ignore all other forces except for friction, then we can make estimates. As the car is driving, the air is flowing past the car, and thus the car will feel a drag force. And we can model that drag force with the standard formulation that we have. It's a drag coefficient, a perpendicular area, frontal area, times half rho r v of the car squared. To find the mileage, we have to equate energy consumption. Energy, or work, is force times path, the length that the path that we're driving, and thus the mileage equals energy per unit of distance traveled equals thus the drag force. If we now have the T Ford and compare that to a modern car, and we let them drive at the same velocity, we see that the ratio of the mileage of a modern car over the ratio of the T Ford equals the drag coefficient times the frontal area as half rho v squared is the same for both. Thus we have the CD A perpendicular for the modern car over CD A perpendicular of the T Ford. And we can look these numbers up, for instance on the internet. You will find that drag coefficients for modern cars are 0.3, whereas for the T Ford, which is much less streamlined, it's about 1. The area, frontal area of a modern car is, if you look on the internet, 7 square feet, whereas for the T Ford that is 28 square feet. And thus this ratio is 1/12. And this shows that old cars, like the T Ford, have a very bad mileage. Modern cars, via their streamline and via their flattening, have a much better mileage. And it also shows what you need to do if you want to improve. Make the car more streamlined. Make it even flatter. Okay, that is one. We see how this works. Environmentalists would argue that you better drive at 90 kilometers per hour rather than 120 kilometers per hour from an environmental point of view. Can we understand that? Can we see how that influences the mileage? Yeah, sure. If we compute the mileage at a velocity of 90 versus a velocity of 120 kilometers per hour, for the same car, what we see is that is thus the ratio of the drag forces at these velocities, but now CD and A perpendicular drop out, as it's the same car, half rho drops out, it's the same air, and you get the square of the velocities. And out of that comes that the mileage goes down pretty quickly if you increase your speed from 90 to 120. You roughly double the amount of energy that you use. From an environmental point of view, you better drive slow. Hope this shows you how you can work with drag forces and answer different questions than only computing the drag force.